In this video, we're going to introduce the concepts of an eigenvalue and an eigenvector for a matrix. So here's the setup. We have A, which is an n by n matrix. So we have to have a square matrix. And then the eigenvalues associated to A are some special numbers that have some certain properties. And every eigenvalue comes with some eigenvectors. And eigenvectors are, as the name implies, vectors. So what kind of vectors am I talking about? I'm talking about column vectors. So here V, and I'll underline it just so that we can remember that it's a vector. This is an n by 1 column vector. And then I'm going to need a scalar. The scalar is going to happen to be my eigenvalue. So that's going to be lambda. And this is a scalar. So this is kind of the setup. And we say that V is an eigenvector for the matrix A with eigenvalue lambda if, well, we need two things. First of all, I need V not to be 0. So if V is the 0 vector, then everything kind of works in a really boring way. So we just rule that out immediately. So V is not the 0 vector. And then we have the following equation. A times V, so A is an n by n matrix. V is an n by 1 column vector. So when I multiply A times V, I get another n by 1 column vector. So A times V, this is going to be equal to lambda times V. So here, this just means take the vector V and scale it up by lambda. So this is what it means for a vector V to be an eigenvector for the matrix A with eigenvalue lambda. Now, you might have a couple different reactions to this. First, you might wonder, why are there any such things? And second, you might wonder, why isn't kind of everything one of these? So let's look at a little example, and we'll see that there are some eigenvalues and eigenvectors. And maybe we'll also see that not everything is supposed to be one of these. So they really are special. OK, we're going to do a 2 by 2 case, because that's something nice and easy to handle. So let's take the matrix A to be 2, 1, 0, 3. And let's take some different vectors. So let's see. U will be the vector 1, 0. V will be the vector 2, 0. And then W will be the vector 1, minus 2. So here I just picked some vectors. And now let's multiply A times each of these vectors and see what we get. So A times U, this is 2, 1, 0, 3 times 1, 0. So 2 times 1 plus 1 times 0 is 2. 0 times 1 plus 3 times 0 is 0. And what we see is we get the vector 2, 0. And that's definitely twice what we started with. So this is equal to 2u. So what we have here is we have an example of an eigenvector u with eigenvalue 2. All right, let's move on to V. Two times 2 plus 1 times 0 is 4. 0 times 2 plus 3 times 0 is 0. So that A times V is 4, 0. And 4, 0 is twice 2, 0. So this is 2v. So what we see here is we've got another eigenvector for the same eigenvalue. So if you have an eigenvalue, it has more than one eigenvector. And here, the relationship between u and v is pretty obvious. V is really just twice u. So if v is an eigenvector with eigenvalue lambda, then so is any non-zero multiple of v. OK, now let's compute a times w. So 2 times 1 plus 1 times minus, that's 0. 0 times 1 plus 3 times minus 2 is minus 6. So a times w is 0 minus 6. And you can see that there's no scalar for which 1 minus 2 is equal to 0 minus 6. For it to work out in the first coordinate, we'd have to have that scalar be 0. And for it to work out in the second coordinate, we'd have to have that scalar be 3. So u and v are eigenvectors with eigenvalue 2, and w is just not an eigenvector at all for any possible eigenvalue. I want to think about one more aspect of this story, which is this eigenvalue 2. So we've shown that lambda equals 2 is an eigenvalue. And I want to take that lambda equals 2 and do something with it. And what do I want to do? I want to take a and subtract off 2 times the identity matrix. This 2 is the same as this 2. And what do we get? Well, we get 2, 1, 0, 3 minus, now the identity matrix is 1, 0, 0, 1. So twice the identity matrix is 2, 0, 0, 2. So I get 2 minus 2 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 3 minus 2 is also 1. This matrix has the obvious special property that the first row and the second row are the same. Or in other words, another way to say what kind of property this has is to say that the determinant of A minus 2 times the identity matrix is equal to 0. So once we subtract off twice the identity matrix, we get a singular matrix. That's going to be very important when we go about thinking, how do we find what eigenvalues a matrix has and what eigenvectors go with it?